In today's lab, we're going to be looking at HPLC. HPLC stands for High Performance Liquid Chromatography. So it is a type of column chromatography. HPLC is sort of a modified type of column chromatography that instead of traditional columns where we just use the force of gravity to allow the sample to travel through a column, HPLC uses a high pressure pump that pushes the sample through the column. So I'm just going to go through and point out some of the main components of the HPLC system. So the one you can see right here on your screen, that is the HPLC pump. Okay, so it is a reciprocating pump. It uses a piston to push the mobile phase through the column and through the system. So on top of the pump, you'll see a number of bottles. These are the solvent reservoirs, so they contain the mobile phase. And the mobile phase can have a varying composition, so it can contain things like methanol, acetonitrile, acids, water, to give us different degrees of polarity. In today's lab, we're just going to be using degassed water with no other additives, so our mobile phase will be polar. So these solvent reservoirs are attached to the pump. You see there's tubes here that go into each bottle to attach to the pump, and when the pump is started, then it pumps the mobile phase through the pump, through the injector, which we'll talk about in a minute, and onto the column. On the left-hand side of the pump, you'll see our injector right here. So that's our sample injector, which allows us to introduce our sample onto the column. So it has two positions, load or inject. Okay, so it's in the load position right now, and that's where we start. So when we load our sample into the injector, we want a specific amount of the sample to enter the column. So it actually has a loop behind it, in back here behind the injector, that is set to a specific amount. Okay, so 5 microliters, 10 microliters, they come in various sizes. So that holds that amount of sample until we're ready to inject. So when we have our sample in, then we move our injector over to the inject position. And what that does is allows the mobile phase to pass through that loop. And when it passes through that loop, it sweeps the sample into the column with it. So when it's in the load position, the mobile phase is bypassing the injector and just going directly onto the column with no sample. When we hit inject, it goes through the loop and takes the sample with it into the column. After the column, we have the detector. So there are various types of detectors available. It could be UV, infrared, a mass spec. There are different types of detectors we can use. In this case, we're using a UV visible spectrophotometric detector. So when our analyte comes off of the column, it is picked up by the detector, which detects the molecules as it enters the detector, and it sends that information to the computer, which contains software that we use to get our peaks. So if we look at our detector here, this is a UV visible spectrophotometric detector. Okay, so it's a really old model, but still works really well, so we still use it. So you'll see that the reading there is giving us negative 0.001. So because there's nothing running through our machine right now, we want that to be at 0. So we're going to change that to 0 by hitting the auto 0 button. And you'll notice down below that auto 0 button, there's a number for the wavelength. So right now it's set at 195 nanometers, so that's what we're going to use for today's lab. The dial underneath is where we control the wavelength. So turning that dial allows us to control the wavelength of the detector. So if we go back to our column for a second, this is our column here in the middle. And these columns come in various lengths, so from 5 centimeters up to 25 centimeters. There's some common sizes. The internal diameter also varies as well. That's usually measured in millimeters. And the components, or what it's made up of, varies as well. So the inside of the column, that's where our stationary phase is. So remember, the mobile phase is the solvent that enters through the pump. The column contains the stationary phase. They're commonly made of silica, alumina, cellulose, etc. They have very small particle sizes, which gives it a very large surface area, which in turn gives us high resolution of our analytes. So as I said, the column material can vary. The outside of the column is made up of stainless steel, so it can withstand the high pressure from the pump, because remember this is high pressure chromatography. So as the mobile phase injects the sample and the sample travels through the column, as the sample travels through the column, the analytes, the molecules in the sample will separate out at different rates. So in this case, we're specifically doing reverse phase chromatography. So the stationary phase, that's the column, is non-polar. So in this case, it's made up of C18, which is a non-polar column. The mobile phase is water, which is polar. So our stationary phase is non-polar, our mobile phase is polar. So the non-polar molecules will be retained longer on the stationary phase in the column, while the polar molecules will be retained more by the mobile phase and will travel through the column faster. So we should see the polar molecules come out as peaks on our software faster than the non-polar molecules. So as the molecules get separated on the column based on their polarity, they are detected by the detector, and then that in turn passes the information on to the computer, and a peak is shown on the computer with respect to the retention time. So with respect to the time, the length of time they spend on the column. So things that move through faster will show up as peaks earlier than things that are more nonpolar that are held on the stationary phase of the column longer. Once we're ready to start, the first thing we need to do is actually turn on the pump. So we turn the on switch on the pump itself, and everything else on the pump is controlled by the software program on the computer. So this is the program right here. It's a FlexAir program. FlexAir is the brand name of the pump. It's made by PerkinElmer. So once we open that, this is the display panel we get. So you can see here we have a couple parameters. We have the time that the pump will run for. We have the flow rate of the mobile phase through the column. And this %A and %B, if you remember when you looked at the solvent reservoirs, there were two different lines that can connect the solvent to the pump itself. So we can do different percentages of each line. So say, for example, we had water in bottle A and methanol in bottle B. We could get the pump to mix those solvents so that we'd have 50% of one and 50% of the other, or whatever percentage we want to choose. Okay, so the machine actually has that capability. For our purposes today, we're just using degassed water for the mobile phase, and that is in solvent reservoir A. So we're going to change this to 100% A. Okay, so in order to change it, we want to edit the pump parameters. So we hit F2 to do that. We're going to leave the time at 10 minutes because that should be plenty of time for our molecule that we're looking for to come out on the graph. So we'll leave that at 10. We're going to change the flow. So I'm just hitting the arrow to get it to go to the next parameter. And we're going to change that to 1. Okay, because I want to slow that down a little bit. 2 is a bit too fast. Enter. And now we're on %A, so I want to change that to 100. Okay, I want 100% A and 0% B. And because I've changed that to 100, it automatically changes that to 0 because obviously you can't have more than 100%. So that's really everything we need to change here on the pump software. A couple other things I'll point out here. You can see that the pressure is indicated up here, so it's fluctuating a little bit because we're not actually started yet. But as we start the pump and run our samples, you'll see that increase. So I'm just going to say return here, and that'll bring me back to the display for the pump. And now that we have everything set, so 10 minutes, 1 mil per minute flow rate, 100% solvent A, we're going to hit F8, which is for start, and our pump starts running. So you can see immediately the pressure starts to increase. Okay. So our pump is started. That means there's solvent running through it. You might actually be able to hear it running in the background. So there's no sample or standard injected yet. It's just pumping the mobile phase through the machine. So through the pump, into the column, and onto the detector. So we're going to run a series of standards. And I have 5 standards here that are already made up. So for HPLC, we need to construct a calibration curve or a standard curve that will allow us to find the concentration of our analyte in our samples. So we run a series of standards, similar to what we've done in other labs, of known concentrations of our analyte. So I have 5 different concentrations here, from 1 to 10 ppm. And if we run all of those standards, when we see the peak for each standard on our software, that'll tell us at what time that peak generally shows up using this method. So then when we run a sample that we think contains that analyte we're looking for, if it shows up at the exact same time, that'll allow us to identify that peak. So we'll know that is the element that we're looking for, or the analyte that we're looking for. So we need to have standards in HPLC in order to identify the analytes in an unknown sample. So now we're ready to run our first standard. So we're going to start with our injector in the load position. So this is load, this way would be inject. We're going to start at the load position. So when we inject our sample, or our standard in this case, into the injector, it'll sit in that sample loop until we're ready to actually inject it into the machine. So I'm going to load 20 microliters of the first standard, the 1 ppm, into the syringe, and then the syringe just fits into a little hole here in the injector. Then we just push our plunger, okay, and now our sample is sitting in that little injection loop. So here's where the software comes in. So we have to turn our injector to the inject position and hit start on our software at the same time. Okay, so let's hit inject, and now we'll go to the software. This is the Peak Simple software. Okay, so Peak Simple is the name of the program, and this will give us a graph for our peaks for our standard curve. So you notice right here there are 4 different buttons. So this machine has the ability to connect to 4 different channels at the same time. We're only using 1 channel right now, and we're using channel 2. So you'll notice here how that has a yellow dot here in the middle. Okay, so when it's on red, it's stopped. When it's on yellow, it's standby. And when we hit start, so this works as our start button, it'll actually turn green. Okay, so when we turn the injector to inject, we hit start here at the same time. So I've just turned the injector over to the inject position. I'll hit start right now, and you'll notice how it turned green, and it says running right here. So on our graph now, very shortly, you'll start to see a blue line come across here, and that's where our peak will show up. Okay, so we're just starting to see a peak show up there at a retention time of about 5 minutes. So because there's only 1 analyte in our standards that we made up, we can assume that this is the peak we're looking for, presuming we don't see any other peaks, which we don't here on our graph. So we can use that retention time to identify the other peaks in our other standards and also in our samples. So now that we know what time it comes out, when we run all of our subsequent standards, so this is just the first standard, we'll run the other 4 as well, we should see the peaks all show up at about the same retention time. It may not be the exact same, but pretty close to the same retention time. And then when we run our samples, we can identify if that analyte is there in our sample by whether or not we see a peak at that same time. We can also look at the concentration of the analyte because we're running a series of standards to construct a calibration curve, and we're going to use the area of the peak as the concentration. So the area under the peak is proportional to the concentration of the analyte in the standard. So we're going to construct a curve based on that, and then we can compare our samples to that as well to estimate the concentration of the analyte in the samples. So this is our 10 parts per million standard, and you can see that this is a very large peak. So I'm just going to zoom out here so that we can get it all on our screen. Here we go. So this is a much larger peak than the previous standard, and that's to be expected because remember I mentioned that the size of the peak is proportional to the concentration of the analyte in the solution. So our previous standard was 1 ppm, this is 10 ppm, so we'd expect it to be about 10 times larger. And you'll be able to see that when you look at the areas that you'll be given in your results, the area under the peak. So the other thing you'll notice here is the retention time. So we would expect it to come out at the same retention time as the other peak did. So remember it was between 5 and 6 minutes. And we see the same retention time here as well. So if you look at the top of the screen, you'll see we're at the end of the peak there now at 5.7 or so. But our peak did show up at about the same retention time as the previous standard. So the next thing we're going to do now that we have all of our standards done is run a sample and see if our analyte peak shows up in our sample. Okay, so we have run our sample through the HPLC column, and you can see that we ended up with 2 peaks here. So now the question is either one of those peaks the analyte that was in our standards? And if so, which one? So how do we determine that? Well, we need to look at the retention time, the time that the peak showed up. So if we look at the first peak here on the left, that one came out at around 3 minutes. So that's not where our analyte in our standards came out. But the second peak, that showed up between 5 and 6 minutes. And that is where we would expect our peak to show up for the analyte, the same as we saw in our standards. So we can determine that this second peak here, this is the analyte, the molecule that we are looking for, the same one that we use to prepare our standard solutions. So we can identify which peak is our analyte, and we can also look at the concentration of the analyte that is in our sample by comparing it to our calibration curve. So we've already run all the standards, we constructed a calibration curve based on that, and we can use that now to determine the concentration of that analyte in our sample. You might be thinking, well, what is that other peak? How do I identify that peak? Well, right now, with the information we have right now, we aren't able to identify that peak. If we have an idea based on what our sample is, its composition, maybe we have a guess as to what it might be, we can confirm that by running another series of standards that contain that molecule and see what the retention time is. If it comes out on the same retention time, then we can identify it. But right now, based on the standards that we have, because we only know the retention time for that one molecule, that one analyte, we can only determine what that second peak is. So that was a brief introduction to HPLC, high performance liquid chromatography. I hope you enjoyed it, and thank you for watching.